Hello and welcome back. Oops. Okay. Stop. Hello and welcome back to another video. Today we'll be looking at physics. So this is a departure from our normal maths videos, and I plan to make more of these physics videos in the future. So in today's video, we'll be looking at LEDs and diodes. Specifically, we'll be looking at LEDs. For the essential content, we'll be looking at diodes. And so this is AQA Physics A-Level Electricity. And we'll start with what you need to know for the exams. The rest of this video will simply be helping you understand why this is the case, but you won't really be expected to know all this for the exam. Okay, so starting off with our essential need to know, so it's not that different from our GCSE knowledge, but so we can see that we have our IV graph here for our diodes. So diodes only allow current to flow in one direction, known as the forward bias, and past a threshold voltage. This is usually a low voltage around 0.7 volts. For every increase in voltage, the current rapidly increases. So this is what you need to know, and you also need to know what the graph looks like. Okay, so let's start off with as to why LEDs have a forward bias. So within LEDs and diodes, we have semiconductors, and these semiconductors, they have conduction bands and valence bands. So for insulators, the conduction bands and valence bands are quite far apart, and for conductors, the conduction bands and valence bands are quite close together, allowing electrons to pass through freely. But semiconductors, that just the right space apart, that the electrons, when given enough energy, can jump from one band to another. So for n-types, the free electrons act as the majority of the charge characters, and for the p-types, the holes, or the missing electrons, they are the majority of the charge carriers. But before you put them together, p-types and n-types have an overall neutral charge. Okay, so between the p-type and the n-type, we have what's known as a band gap, and we can see that in our diagram here. So this is our conduction band and this is our valence band. So a lot of our electrons are up here in the conduction band. For our n-type, well, some of them are in the conduction band. The majority are in the valence band here for p-types and n-types. So what happens is that the electrons go from the conduction band here, they move over to the p-type, and they can drop down to the valence band here. So initially what happens is that our first few electrons here, okay, so our first few electrons here, they pass over and they diffuse like a gas. So they pass over and they drop down into the valence level here. But what happens is that the two sides of the barrier between the p-type and the n-type, they become positively and negatively charged. So what happens is an electric field is created, which then prevents electrons from being in the conduction band, and it means that there's only electrons in the valence band. Okay, so they can no longer flow between these 2 points. So now what we need is a potential difference supplied by battery, and this voltage in the forward bias is required to shrink the depletion region, So our depletion region, this is where it's really hard for the electrons to pass over from the N type to the P type. And this is why when we have our forward bias, the depletion region shrinks. But in our negative bias, the depletion region grows, as when we connect our negative terminal of our battery, we're pushing our electrons here, pushing our electrons towards the p-type, and when we connect our positive terminal there, we're pushing our holes this way, so that the electrons can drop down and they can conduct throughout the circuit. So for LEDs, when our electrons drop down to the lower valence band, they emit energy in the form of photons. And this is what we use for our LEDs. So if we can take a look here, so I'm not sure if that's going to pick up very well, but essentially for our LEDs, we have a small sort of half a sphere, I guess, where the semiconductor is located, and we have a casing for the light to shine through. And now we can move on to looking at different LEDs. So if I switch this circuit on right now, we'll notice that the blue LED is shining a lot brighter than the red LED. But this is because this red LED actually broke when I connected it directly to a 6-volt battery. It started glowing extremely bright, and then it broke. That's the same happened to this red LED here, and basically sort of due to this how hot it was getting, it basically snapped the casing in two, and there was a bit of smoke. So why is this the case? Why can the blue LED handle the higher voltage and the red LED can't? Also, as a side note, you should never connect an LED directly with a power source. There should always be a resistor. As we can see, past the threshold voltage, for every increase in voltage, there's a rapid increase in the current. So your LEDs are going to be pulling a lot of current, and without a resistor to limit the amount of current they can pull, it can really damage the LED. So looking at this equation over here, so our LEDs, they emit wavelengths so they emit visible light. So to determine what color they are, so as we can see here, different wavelengths correspond to different colors. Shorter wavelengths is blue, longer wavelengths, that's red. So to determine our wavelength, we can do our Planck's constant times speed of light in a vacuum. So today we're not going to look at our Planck's constant or dive deeper into this. We can for today's video, just think about it like a constant, really. And this is all divided by our band gap energy. So this is the difference in energy between our conduction bands and our valence bands. And if we assume 100% efficiency, our band gap energy, which is the energy of the electrons moving from the conduction band to the valence band, that's equal to the charge of one electron. So I think that's what, 1.6 times 10 to the power of minus 19, but that figure might not be right, times by our forward voltage, and this is essentially our energy that can be gained or lost when our electrons moving between conduction bands and valence bands. So now we have an equation where the wavelength is equal to Planck's constant times speed of light. Should add a times here. and then charge of electron times the forward voltage is equal to the wavelength. And we can see that if we increase the voltage supplied to our LED, we're going to get a smaller wavelength. So if I have an increased voltage, I'm going to get a blue light emitted. But if I have if I apply a smaller voltage, I'm going to get a red wavelength. So we can see this is why blue LEDs require more voltage than red LEDs, because they have bigger band gaps and therefore they emit a shorter wavelength of light. And this is also why our first LEDs were infrared LEDs, because we could easily make small band gaps. But for blue LEDs, the band gaps were quite large, and this is what the difficulty was in blue LEDs. And if you want to look deeper into this, there's a video by Veritasium where he looks at the history of blue LEDs, and I would highly recommend it to anyone who wants to know more about LEDs. So that's the end of today's video. Next video will be back to maths, and it will most likely be on logs. And I hope you enjoyed watching this video. As always, please like, comment and subscribe, and thank you for watching. Goodbye.